Welcome. So today we're going to be talking about the atom, the most practical aspects of an atom. We're going to be talking about what's inside the atom and some useful properties regarding the atom. This video, we're not going to be doing so much of talking about how we got to the idea of the atom. That'll be for a different video. What we're doing here is we're just going with all those past experiments that established the atomic model that we have today, and we're just going forward with it and just talking about the most basic properties of the atom. Okay, but in a nutshell, the atom is the most simple building block of matter. Right? So atoms, they're really small. We're going to show those sizes in a moment, but the atom, actually, you can get smaller than the atom. The atom itself is made up of three possible particles. We have protons, neutrons, and electrons. The protons and neutrons, they form what's called the nucleus. That's going to be the core, the inside of the atom. And then we have electrons, which is the outer part, the outer shell of an atom. So I listed some relevant information here for the proton, the neutron, and the electron. Let's start with charge. So without going too deep into physics land, I wrote these technical details down here. But basically, I'm just saying, whereas elementary charge is known as 1.602 times 10 to the minus 19 coulombs, that is often a really cumbersome number to work with. So instead of using this, we just say, okay, let's just call that an elementary charge, and a proton has an elementary charge of 1 plus. That's way easier to say and work with. So we got the proton with the 1 plus, neutrons, well, they're neutral, they have no charge, and electrons have the 1 minus. You may be wondering, how come you're not saying plus 1 or minus 1? Or if it's positive, why are you writing a positive sign at all? When it comes to charges, we write what the sign is, whether it is a positive or a negative. We still write the positive, even if we know it's a positive number. We still write it. You may also be wondering, why do we write the positive or negative to the right rather than to the left? Well, that is customary in chemistry to write the positive or negative sign of charge to the right. In other words, by writing it to the right of the number, that's how we know that we are talking about charge versus some other regular positive or negative number. When you see a positive or negative sign to the right, you're like, oh, we're talking about charge. All right, next up, we got the mass. And again, like we did with charge, we made these easier units to work with. The atomic mass unit is something that was made to make masses easier to work with for these really, really tiny particles. An atomic mass unit, in case you're interested, is 1.6605 times 10 to the minus 24 grams. But instead of writing that all the time with annoying, cumbersome powers of 10, sometimes you need it, but usually not really when talking about these masses. We got atomic mass units instead. So important to note that the proton and a neutron, they both have masses of almost exactly one atomic mass unit. You can see why maybe the AMU was a convenient thing to develop. You may be wondering, how come it's not exactly a 1? That is a topic for another time where we're going to be talking about isotopes, mass defects, things that if I talk about anymore, I'm scared of scaring you in this moment. So just for now, these are both basically 1. And you can see that the neutron is just a little bit more massive than the proton, just a little bit. Now, this part's interesting. Look at that electron mass and how small it is. It is much, much, much smaller than that of the proton or the neutron. If you did the calculation of taking that electron mass and dividing it into the proton mass or the neutron mass, you would see that it's about a 1 to 1,800 ratio, almost 1 to 1,000th the mass of a proton or neutron. So we'll talk about this several times, but the mass of the electron for most aspects of chemistry is considered really small or just negligible. We often don't even really think about it, but technically it's there, just not much. This last column is interesting. I felt like I had to put radius in quotes because when measuring something like size, it gets more difficult when you're talking about small things. It gets really, really difficult when you're talking about like really fundamental parts of matter. All right. So that being said, we can try to assign some sizes to some things. You can see with the neutron, I don't have anything there, but for the proton, we get a size of 0.831 as an approximate radius for it. What does this number actually mean if you're interested in reading up on the physics? Well, that is a measurement of charge distribution, okay? How the charge is distributed in the proton. Okay, they get this 0.831 distance. All right, and this has been revised a few times in the last maybe 30 to 40 years. There's been a lot of good science coming out here in the last maybe 10 to 15 years. So maybe even the last 5 years. So this is an interesting, this is still the subject of some sort of scientific debate. But that's the number I'm putting forward. I'll put the link in the description for how I sourced that number. All right. There was a similar attempt for looking at charge distribution in a neutron. You may be wondering, wait, it's neutral. Where's the charge? Well, we'd have to then talk about quarks being the building blocks of hadrons, like the proton and the neutron. Yeah, you can get even smaller than a subatomic particle. Not very practical at the Chem 101 intro chem level, but you can. There is some work being done on that. There's, I think, some consensus of how the inside of a neutron is positively charged and the outside is negatively charged, but the charges overall add up to 0 between the up and down quarks. So they've tried to measure kind of that charge distribution, but with me trying to read enough science before publishing this video in a reasonable amount of time, I didn't arrive at any number I was really comfortable writing here. Okay. This last one, the size of the electron, 2.818 femtometers. What's a femtometer? Oh, I forgot to say that. It's a really dinky distance, 10 to the minus 15 of a meter. So we have a decimal point, 14 zeros, and then that 1. Okay, really dinky. But we can see that this radius distance is larger than that of the proton. However, I want to throw some caution here. This electron radius, that is based off of a distance of the an amount of distance for light, okay, photons to interact with an electron. In other words, about how wide of a distance is needed in order to interact with an electron. So that's not measuring charge. Electrons have no charge, and they're a fundamental particle if you want to read up on particle physics. But and nonetheless, it gives some sort of sense of scale of the practical limits of working with any of these particles. Okay. So hopefully that wasn't too much physics. Unless you love physics, then there you go. But the takeaway I want you to have here is that when it comes to atoms or subatomic particles, we're really working with really, really small, tiny distances, femtometers. All right, so small masses, small distances. Now let's put these all together into an atom. Yay, last slide already. So we have the Bohr model of the atom. Okay, as we'll talk about later, the Bohr model of the atom is just an approximation. We'll talk about wave mechanics, quantum mechanics, how that is going to give a more better description of the atom that describes data better in terms of how we observe the atom. Okay, wave mechanics, and we'll talk about probability clouds and stuff. For today, let's just push that to the back burner. Thinking of an atom in terms of this Bohr model is often a lot easier to do, and sometimes that's really all you need. Okay, the earliest descriptions of atoms were like them kind of being like planets in terms of how they're built. You have this nucleus, like a star, like the sun, and then you have planets going around your sun, right? And those planets could be electrons in our analogy. So that's kind of the Bohr model. So in that same idea, if you have like a sun and a planet orbiting it, it's a balanced act between gravity pulling in that planet to the sun, but also it's not getting pulled in because it's in constant motion, and that constant motion is able to prevent it from colliding into the sun immediately. All right, similar idea here, but kind of not really either. Unlike gravity, which is how masses get attracted to each other, a completely different property is at play when it comes to an atom. We have something called the electrostatic force, also known as the Coulombic force. And that's the simple idea that plus and minus charges attract to each other. Okay, that's just a property of charge. And then if you have like charges, like two pluses, they're going to repel. If you have negative charges, they're also going to repel. In order to have an attraction, you have to have opposite charges. Okay, that's a charge property. All right, so that's what's holding the electron close to the nucleus. We got this nucleus in the center of the atom, and like really tiny. If I were to scale this up, it's like dropping a pea in the middle of a stadium. So really, really, really tiny, the nucleus. And then we have electrons being held close to the nucleus by this electrostatic attraction. All right. So we can have this measurement or calculation of a Bohr radius going from the center of the atom to the outside. And past a Bohr radius, the electron isn't really attracted to the nucleus anymore. So you can think of this as like a practical distance for where the electron can be in relation to the nucleus. Okay, that's kind of our electron cutoff, not attracted anymore. So that forms a pretty good practical distance. Now check this out, 53,000 femtometers is that Bohr radius compared to those really dinky femtometer distances earlier. So there is a lot of space for these electrons to be in relation to the nucleus. All right, so here's the paradox takeaway for the end of this video. Most of the mass of an atom is that nucleus where you can find the protons and the neutrons. Electrons have very little mass. However, most of the space of the atom is where you can find the electron. All right, and I'll kind of leave it at that. We'll discuss in a future video how we came to know, how we knew the protons and neutrons were in the nucleus, how we know electrons to be on the outside. But I think that's about it for now. All right, thank you very much and have a good one.